But welcome to the first ever Sin City Programmers Group. You might be thinking, all right, raise your hand if you've been to the Sin City Programmers Group before. Is anyone raising their hands? No.
Isn't that technically impossible?
I believe that's technically impossible because this is the first one.
Yes.
This slot was the Vegas Programmers.
No, it's the Programmers Group. You got to make the index 0 based.
Oh, true.
Oh, it's the
Sorry.
Okay, well, so we went with the name Sin City Programmers. We may very well change it later, but we wanted to make sure we were clear that that there was the distinction here. So we've got, we had one person that was going to be presenting today I was super excited about, and then they had something come up, and that's understandable, but hopefully next month they'll show up. But we have, Richard Kiss is going to present on Lean 4 programming language. Anybody familiar with it already?
Probably not.
Good. This should be very productive. And without further ado, we'll leave it to none other than Richard. Big round of applause for him. Biggest we can do it. Yeah. All right.
Thank you. There we go. Localhost 8000 is now full screen.
Yay.
Thank you. That only took 1 minute. Okay, today I'm going to talk about Lean 4, which is a programming language that's also a theorem prover. So it's going to be a lot of math. Hope you guys like math. And I'm going to touch on how Lean is changing mathematics and mathematical computer science. So public service announcement, vote if you're eligible, and most US citizens are. Vote. Because Nevada is a swing state, Nevada presidential votes count more than most other states by a lot. In fact, according to 538, they are the most powerful by a significant factor. So use that power while you can. So let's talk a little bit about me, because why not? My name is Richard Kiss. I am Canadian, grew up in Canada. Thank you.
That's where Canadians grow up, yes?
Yes, that is where a lot of them do. That's true. I love computers. In fact, I think I've loved computers before I knew what they were. Quick story, when I was 5 or 6 years old, my mom was taking a class at the local community college, and they taught her binary for whatever reason. So she came home. I already knew how to count in decimal. I didn't know it was called decimal. And she taught me binary. And I was so excited that I wrote the numbers 1 to 500 in binary next to their decimal equivalents in a giant table. Pretty messy. And no good deed goes unpunished, and in this case it turns out I made a mistake at 256, I believe, and all the subsequent numbers were incorrect.
Oh.
Anyway, also I am, when I was young, I was good at math contests. It was a natural skill that I had. Probably not that surprising when you find out that I was excited by binary at age 5. In fact, being good at math contests became a big part of my identity to some degree, and I studied mathematics in college as an undergraduate and graduate student because I was lazy, and I figured it would be the easiest way to get good grades because I was so good at math. I'm old. I have over 40 years of computer programming experience, including game development and game hacking. When I was a kid, I deprotected a lot of games on the Apple II. One of my first jobs out of grad school was reverse engineering Super Nintendo games in the mid-90s, making them work with a video game modem. No source code. They gave us a cartridge, you plugged it into this thing, you started disassembling things, trying to figure out how it worked, trying to figure out where it read the joystick so that it could talk to over the phone line, send the joystick values so the two machines would run in sync. That was a crazy job, and no one cared. Then I worked for a healthcare company, did a lot of embedded C and C++ for an appliance that they were developing. And I did some web development in the early 2000s before anybody really knew what web development was using Apple's web objects, which was way ahead of its time. It's now gone. It didn't really keep up. And I haven't really kept up with web development. I'm not good at JavaScript. If I were doing web development, I'd probably use Python. I'm a curious fellow. I like to know how things work. And it's really not so much liking, it's I must know, to the point where I can't help myself.
A compulsion.
Yes, compulsion. That's a good way of putting it. Here's some things that I like. Python and Mojo. Mojo, I don't know if you've heard of it, but it's a compiled language that's like, it is to Python what C++ is to C. And it's a real thing. It's going to be fast. It's created by a guy named Chris Latner, who formed a company called Modular. Chris Latner is the creator of LLVM, which is used by, it's the compiler framework that powers Clang, Rust, Swift. And once Mojo's done, I think it's going to be really important. Maybe I'll talk about that in a future episode. Is that what these are called?
Yeah.
I'm really interested in Bitcoin. Back in the early 2010s, I was fascinated with it, reversed engineered it enough to create a Python toolkit called PyCoin, which some people actually still use today. Over 1,000 stars on GitHub. It's probably the best thing I've ever done. It's just sad that it's in my head, but that's life. What else? Oh yeah, I like Rust. It's the main systems programming language that I believe through its design actually has a chance of being memory safe and thread safe. I think Mojo may challenge it, but Mojo is still immature. Rust is not. Because I'm curious, I read Hacker News every day, and I do a lot of clicking on Hacker News. I don't know if you know what Hacker News is, but you should. So I like Git, Unix, macOS, command lines, Vim, emulation, self-hosting LLMs, minimal code bases, blah, blah, blah. I just like knowing how things work. And I like Lean. Lately, I've been pretty obsessed with Lean. So that's what I guess that's what I'm supposed to be talking about, right? Not me. Anyway, so what I'm going to talk about is Lean. I'm going to talk about what formal mathematics actually means. We're going to go through a simple example of formal mathematics, adding whole numbers. You know, what's 2 plus 1? Anyone?
3.
That's right, 3. But why?
Because.
Well, we're going to find out. And then we're going to do the formal mathematics in Lean, the programming language that knows math. Okay, so Lean is a programming language. First, you can write code in Lean that looks a lot like Haskell. Anybody know Haskell? No? Anyone heard of Haskell? Yeah, okay. I've heard of Haskell. I don't really know it. I probably could learn it pretty well because I know Lean good, but I don't know much about that. It's a way to do formal verification of programs. Now what that means is it lets you prove properties of code that you write. For example, if you write a list.append function, you can prove that the length of the list goes up by 1. You know, it sounds trivial, but have you ever written a program? Have you ever proved that about a program, that the value goes up by 1? Probably not. And it also proves mathematical theorems, and that's really its killer app at this time. That's much more mature than actually verification of programs. And Lean, and finally, Lean is 4. I'm going to be talking about Lean 4, and the reason it's called Lean 4 is because I suppose there was Lean 1 through 3. I know about Lean 3, I don't really know about 1 and 2, but I imagine they probably existed. Lean 3 was implemented in C++. Lean 4 takes a little different tack. It's got a core implemented in C++, and then it implements most of itself in Lean. So there's about 10,000 lines of C++, and then a ton of Lean, which is implementing Lean. And that's what Lean does. In fact, it's sort of a complex macro parsing system that's extensible, which means that users can easily add new syntax to the language. So when you import a library, you can get new syntax. And one thing that this does is it lets math code look like math. So here is an example. Is that legible? Yeah, that's not so bad. Sorry about the gray scale there. Why is it not? Yeah. On my screen it's in color, so I don't know. Who knows? Anyway, so this is an implementation of a command line tool which prints Fibonacci numbers. You know, Fibonacci numbers are, it's a sequence where you start with 1, 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 8 plus, where am I at? 5 plus 8 is 13, 8 plus 13 is 21, and so on. This is a terrible way of calculating the Fibonacci numbers. Don't do it this way. It's recursive, but it's recursive order n squared, and you could do it recursive order n. And most of this code here is actually just dealing with the I/O and the error cases. So you may not know what everything here does, but you can probably look at it and say, yeah, I know enough of what it does that I'm convinced that if this actually compiles, it probably does print Fibonacci numbers. Another thing about Lean is it supports Unicode natively, and it uses it quite a lot because They want it to look like math. So a lot of math symbols you'll see in here, like the first one, the little hat, that's an and then the upside down hat is an or, and then not, and then the upside down A means for all, you know, like if you're doing mathematical proofs, and then there exists, and then subset inclusion or equality, set inclusion, set not inclusion, empty set, natural numbers, integers, rationals, reals, complex numbers, plus minus. There's a whole bunch. But yeah, it's great if you want your math to look like math. It's got a functional, Lean has got a functional programming paradigm. Now what that means, like Haskell, is there are no side effects at all, which means every time you call a function with a certain set of arguments, the same thing always comes back. You can't go to the file system, you can't go to the internet, you can't, I don't know what else, you can't look at the time. None of that can impact the output, which means that you can cache arguments, and if you ever see those arguments again, you can just return the last calculation, especially, which is useful if the calculation is expensive, like it would be in that Fibonacci case. Now, if you think about this hard enough, you realize that no side effects means how do you print to the screen or do file I/O? And there's this trick that Haskell and Lean and several other functional programming languages use called monads. And maybe you've heard the term monad, and maybe you've tried to figure out what it is, because that's what happened to me. Is the first time I heard the term monad, I looked it up, and I didn't know what the hell they were talking about. And then I heard it again, and I looked it up, and I still didn't know what the hell they're talking about. So if you're interested in monads, I encourage you to learn enough Haskell so that you can start trying to figure out what a monad is, because if you can ever get through that, then you can feel proud of yourself. Eventually I figured it out. I know what it is now. I like to describe it as a monad is like a deep concept that hides away global state. So when you do a print or a file system access, where's that example that we had? Oh, it's up this way. No, I forget where it is. I'm trying to find the Fibonacci thing. Oh, there it is. Up arrow. So you see I/O print line. What that's doing is it's feeding in this string. Oh, I guess you can't see what I'm pointing at. I'll just stand up here. This string is expanding and being fed into the I/O monad. And the I/O monad basically eats the print line and remembers that it's got to do that. And then when main returns to some runtime wrapping code, it looks at the monad and figures out, oh, these are all the things that I have to print and calculate, and this is how I do it. And then it does it. So your program is sort of turned inside out. When it runs, really what it's doing is it's collecting up the computations that it needs to do and what it needs to, the side effects that it needs to perform, whether it be file system I/O or file system or some other type of I/O, and it does it. So it's very bizarre. So hopefully I've made the concept of monads interesting and probably more confusing than when you knew nothing about it. Lean also supports higher order functions. I don't want to talk about this right now. Okay, let's talk about formal mathematics. Formal math is annoyingly pedantic, which, as you might guess at this point, is right up my alley. It's the foundation of mathematical rigor. It requires precise definitions, clear assumptions, and logical arguments. So no futzing around. Your axioms are the explicit assumptions. Axioms are things you start with and you assume to be true. And in pure math, the axioms that you start with tend to be pretty banal and fairly non-controversial, like there is a thing. That might be one of your axioms. Or two functions are the same if when you put the same input into each, the same output always comes out. That seems pretty non-controversial, right? And another thing about formal mathematics is you want your definitions to be extremely precise. Once you have your definitions, you have mathematical objects. What professional mathematicians like to do is figure stuff out about them. So you have your axioms and you figure out what must be true if these axioms are true? And so you have to take logical steps from your axioms to your theorems. Every step is justified, no appeal to intuition. And so if you discover something new in your professional mathematician, you publish it in a paper, and it's verified by peer review, where other people read it, they look at it, they look for errors, they build upon the results, they discuss it, whatever the hell. And verification is hard. This example is from a paper by Andrew Wiles, the guy that proved Fermat's last theorem, a theorem that was unproved for like over 200 years. He proved it in the 90s, and it took him 2 cracks at it. The first one, he did it, and then a couple years later, they found a mistake, and they had to go back and repair it, which sounds totally bizarre thinking about repairing mathematics, but it's a thing that happens. Anyway, this paper is over 100 pages, and most of it looks like that. So as you might well guess, not many people understand the whole thing. Probably fewer than 10 people have checked the entire thing. 10 people in the world. And if you want to make that sound even more dramatic, 10 people in the universe. Because most people in the world are in the universe. Where's my cursor? There it is.
And you verified that statement.
You verified it? Awesome.
Verified that statement.
Well, let me ask you, what's the co-cycle? Okay, too slow. Anyway, so this checking by peers step can be a real problem. You know, new ideas are often published in journals that are not read by many people, and the gritty details matter a lot because any flaw in reasoning can ruin the entire proof. And unlike computer code, there's no compiler that you can run a proof that you can run on a proof to check that no details are missing, unless you write it in something like Lean. So let's do an example. Let's talk about the natural numbers. Let's describe them axiomatically. Okay, so first off, natural numbers are what you might think, 0, 1, 2. We're computer scientists, so we'll start at 0. 0, 1, 2, 3, up to infinity. So there's 4 axioms. With these 4 axioms, you completely define natural numbers. So the first axiom says 0 exists and is a natural number. So you have a 0. The second axiom says if you have a natural number, there's this function called next, which bumps up the natural number to the next one. So next of 19 is 20. Next of 600 is 601. Next of 9 is?
10.
Yes, correct, 10. I heard 10. It's pretty exciting stuff, huh? Anyway, now number 3 says if you have 2 natural numbers and their nexts are the same, then the 2 natural numbers are the same. And you might think, well, why do you need that? You need this because otherwise 0, 1, 1, 1, 1 works. And that doesn't look like the natural numbers because there ain't no 2, for example. So if you do that, 3 doesn't work because 0 and 1 in this case have the same next. They both have 1. So 3 kind of says next always gives you a new thing. Well, it's halfway to saying that. You also need number 4, which says that, well, actually, I guess number 4 doesn't say next always gives you a new thing. Number 4 says that next never gives you back 0. Because otherwise, a clock would work where you have a 0 at the top and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then next of 11 is 0. So it just wraps around like a pinball machine. And although that does satisfy 1, 2, and 3, it's not what we think of when we think of the natural numbers because we want infinity of them, not 12. Okay, so using this definition of next and 0, the natural numbers now look like this. There's 0. There's next of 0, often called 1. Next of 0, often called 2, and so on. And now let's define add. So this is going to resemble what we think of as addition. But we're going to define it in a very precise way using as few steps, using as few axioms as possible. So we're going to do it with exactly 2 axioms. The first one is the axiom of add 0. When you add, so add is a function that takes 2 numbers, right? You know, add of 3 and 5 is 8. So add of 0 to n is always n. Not controversial, right? That's what we want adding 0 to mean. We're not going to bump up n at all. It's just going to stay the same. And now axiom 2 tells you what happens if you're adding a number that isn't 0, a number that has a next, right? Everything has a next except for 0. So every natural number is either 0 or the next of something. So in the case where it's the next of something, what you do is you just figure out what it is, what the addition is without the next of that thing, and then do the next afterwards. So you're sort of pulling the next out, right? Let's check it out here. Add 3 and 2. Well, 3 is next, 0, and 2 is next, 0. So you pull out the first next, you pull out the second next, you pull out the third next, you pull out the fourth next, and then you're left with add 0, next, which we know when you add 0 to next, 0, you just get next of 0. So now you've got 5 nexts in a row. So essentially what you do is you bump down the first argument until it hits 0, and then the add and the 0 just go away. Because add 0 of anything is that thing. So that we've proven that 3 and 2 are 5. Huh?
How about that?
Do you think you're going to do that when you got up this morning? Okay, so now let's actually prove a theorem. We've defined what natural numbers are using those 4 axioms. We've defined the function addition using 2 axioms. Let's prove that when you add n to 0, you get n for any natural number n. Now the first thing you might think is, what's the big deal? Isn't this obvious? Isn't this obvious from the definition of add? No. The definition of add that we've agreed upon says when you add 0 to something, you get that something. It doesn't say when you add something to 0 what you get, right? If you have a function that you've written in a file, you can't just swap the 2 arguments. You don't know you're going to get the same thing back. We haven't proven that yet. So, all right, sorry, here's the definition. So you see how it's different from the definition. You can't simplify this using the first rule. You have to simplify it using the second rule. Well, actually, that's not quite true. There's really 2 steps. N is 0, and n has a next. N is a next. So let's look at the first. Let's look at the n equals 0 case first. I just want to comment. This is you may have taken a math class where you learned about proofs by induction. This is a proof by induction. It's closely related to recursion. Essentially, a proof by induction works like this. We want to prove this for every n. So you can think of lining up a bunch of dominoes on a table. The first domino corresponds to the proof for 0. The second domino corresponds to a proof for 1, and then 2, and so on. So there's 2 steps to proving it for every single domino. You prove that the dominoes are close enough together so that if you have a proof for the 5th domino, it falls over and hits the 6th domino and gives you a proof for the 6th case. So you show the dominoes are close enough together, and then you knock over the first domino. And then you're done. So you have to prove the special case 0, but because you know that proving 0 proves next of 0, which is 1, then you proved it for 1, and then you know that if you proved it for 1, then it works for 2, and so on. It's pretty kooky. The first time you see this, it's quite bizarre. Anyway, so as I say, there's 2 cases. There's n equals 0, and for this we know the theorem is true because add 0n is defined to be n. So add 0, 0 is clearly 0. So that's how we knock over the first domino. Now say we have a proof for domino number k. So since we have that proof, we know that add k0 equals k. And in this case, this is the case where n has a next. N is next of k. We want to show that add n of 0 is also n. So n is 1 more than k. Okay, well add n of 0 is add next of k 0, right? Because n is next of k. Simple enough, just simple substitution. Now we can pull out the next, because that's the rule of how addition works. And add k of 0 is next of k, because we've already proven that. That's one of our assumptions. And we know that next of k is n, so you can compress all this down to add n of 0 equals n, which is what we're trying to show. And there you have it. You've now proven that with this definition of add, that when you add a number to 0, no matter what number it is, you get that number back. So it seems like a lot of yelling for no reason, but there actually is something deep here. Okay, now let's talk about how you do this the same example in Lean. This is how you define the natural numbers, also called whole numbers, in Lean. So inductive, that's like a fancy way of doing a struct that's self-referential. So we define nnum of 0 to be a special nnum. It takes no arguments. It's a constant. And then nnum next takes an existing nnum and gives you a new nnum. And that's it. That's the whole thing. It's basically axioms 0 and 1. For some reason you don't need, axioms 1 and 2. For some reason you don't need 3 and 4, and I haven't quite figured out why. I think maybe Lean just makes no assumption, or just assumes that next always gives you a value that you haven't seen. Then you do the definition of add here. It takes 2 natural numbers and gives you a new natural number. So there's 2 cases. The first natural number does not have a next, it's 0. And B, that just gives you B. Or the natural number does have a next, which we're calling A. And so you can just pull the next out. And that's it. Lean is happy with that, and it can figure stuff out. So this is what the proof of add n and 0 equals 0 looks like in Lean. And it's not that long, but I mean, this isn't too hard a proof. And you can see there's the 2 cases. There's the 0 case, which ends up giving a formula 0 equals 0, which RFL, that's called a tactic, but I think what I'm going to do here is I'm just going to do a demo. So I have, what's happening here? Is it opening? Yeah, I'm using my phone's internet, so who knows how long this will take to load. I should have cached it. There's a thing called live.lean. Is it org or com? I can't even tell.
Org.
Oh yeah, live.leanlang.org. And I'm passing in a URL with a bunch of text, and it's going to decode the text and then just give me there we go. Okay, it's a little small. Let's see if I can make this bigger. Okay, so this is what using Lean looks like in practice. Typically, you do this in VS Code or VI. I think there's some way to do it in anything that has a language server. I haven't gotten around to getting it to work in VI, so I grudgingly use VS Code. On the left is your editor, and then on the right is what's called an info view, where it gives you live feedback about what you're doing. So one example, something you can do is you can eval 5 plus 3. So it actually knows about numbers on its own. And you can see over here it's saying 8. But you can also do something, because this is a functional language, types play a huge role. So there's this other feature called check, where you pass in an object and it tells you the type of that object. So the built-in type for unsigned ints in Lean is nat, short for natural numbers. And it actually behaves more like a Python integer, well, except for it doesn't support negative, in that it never overflows. So you can do crazy stuff like 5, how do you do power? I can't remember if it's 2 stars or if it's hat. Let's just try 2 stars. No, it doesn't like that. Let's try hat. Yeah, there it is. Oh, but I'm checking it instead of evaling it. Let's eval it. Wow, what a number. You got to scroll to see it all. And look, it ends with a 5, as you'd expect a power of 5 to do. Question?
Will it automatically uptype to like a real, like operations in the reals?
Good question. But
So
the
hold up.
The answer is no.
Okay.
Oh, the question is, will it automatically, what did you call it?
Uptype.
Uptype? Yeah, cast to a reel. And the answer is no. Actually, maybe that's not true. if you pass it nat into a function that's expecting a real, I think it probably will cast to a real. But functions tend to be very strict on what they're expecting. So it generally doesn't happen by accident. Like if you took the log, I don't know actually if this supports log, because one thing mathematicians don't like is approximations. That's for physicists. So taking the log of a number, you just leave it as that. Log 5 is log 5. I don't want to see 2.2 or whatever the bullshit that is. Okay. Anyway, here's that definition. Where's the cursor? There it is. Here's the definition of nnum. All right, it's happy with that. Here's the definition of add. And then I've defined a couple other things here. I'm defining 0, just giving it a short name, so that's 0. And here's 1, that's the 0 of next, which is syntax sugar for nnum next 0. And then here's 2, 1 of next. Probably none of this is too surprising. And then here's 3. How am I doing on time? My thing says 30 minutes, but I figured if no one else is here, then...
Yeah, go as far as you think makes sense.
Okay. Well, that ship has sailed. So here's an example of how you'd write a theorem. 0, add 0, and 0 is 0. There's a lot of punctuation here you sort of have to get used to. It's just functional languages. Now, when you're writing code, you just write the code. But when you're proving a theorem, there's this thing called tactics mode, where you type by, and that gives you access to a whole bunch of tactics in Lean, which is, the idea is it's supposed to sort of correspond to how mathematicians think. Like if you have a polynomial with a lot of plussing and minusing and exponentiation, you might want to just multiply it all out, simplify the expression. So there's a tactic called simplify, which has sort of a canonical representation for objects in a way that's supposed to be as simple as possible so that terms cancel, for example. If you have a +3 and a -3, you want those to just go away. Okay, so if you look, I'm going to go to the beginning of the line here. Your goal, what you're trying to prove so far, is add 0 and 0 is 0. You can think of a theorem proof like a maze. You have some inputs, which is the start of the maze, and you have a target, which is what you're trying to prove, which is the end of the maze. And anyone who's solved the maze that's large knows that the best way to solve a maze is to work from both ends and try and meet in the middle. So some tactics work on the front, and some tactics work on the back. So basically, some tactics go into the maze from the front, and others come into the maze from the back. Rewrite 0, that means take the definition of 0 and actually apply it. So here's the before, add 0 and 0, and here's the after. You're looking over here. Add num0 equals num0. It's replaced it's basically expanded this out to that. So that'd be kind of like where you see in an equation x equals 3, and then you substitute all the x's with 3's. And now unfold add. That takes this function and it unfolds it. It actually applies it. So this is the before. Add num0 equals num0. And this function has got 2 cases. And in this case, in this instance, we're going to use this case here, line 13. I guess I can just say line numbers. I don't have to point. That's the great thing about natural numbers, huh?
Next of 12.
Yes, next of 12. Thank you. Okay, so now we have num0.0 equals, nnum.0 equals nnum.0. And RFL, that stands for reflexivity. That basically, if you have A equals B and the proof already knows that A happens to equal B, RFL will take care of it. And this one is actually really powerful. In fact, if you want to prove that 2 and 1 equals 3, RFL is enough to do it. But I did 2 and 1 equals 3 a different way, so you can sort of see what these tactics do. Here's a simp of add. So you see when the cursor is here, this is the current state is that, and then when I go Control E and move to the end of the line, the state changes to that. So what it's done is it's simplified as much as possible based on the definition of add and the definition of, I guess the definition of two. Oh, it also hasn't, oh, that's right. I didn't tell it to simplify 3, but it does that on the next line. And so I simplify 3 and it replaces it with 2 next. And then I simplify 2 and it replaces it with 1 next. So now it's 1 dot next next equals 1 next next. So that's obviously, those two things are obviously equal, so RFL. And then here's the proof that n plus 0 equals 0, and it looks, we saw that earlier. I don't want to get into this too much because I've probably yapped enough. Now, an interesting thing is you can print the axioms that you're using for add, and it'll summarize all the axioms that are being used, and it turns out there are none. All it's using is the definition of add that I used up there. But the axioms used in proving NN add 0 are, there's this one axiom called prop X, which I think stands for proposition extension or something like that. Anyway, it's very complicated, and what I should have done is ask ChatGPT to explain, like on 5, what prop X is, but it's fairly non-controversial. Yes?
How good is it at understanding if you try to provide it internally inconsistent set of axioms?
Well, if you've taken any logic, if you
Repeat
have
the question?
I'm sorry.
Or I can give
How
you
good
the
is it? Yeah, just give him the mic.
Yeah, speak into the mic.
How good is it at discovering if you've provided it a internally inconsistent set of axioms?
Sure. Well, a feature of logic is if you have 2 assumptions that are contradictory, you can prove anything. That's called an inconsistent set of axioms. So Lean supports proof by contradiction. A lot of times you have to do that.
Reductio ad absurdum.
Yes, RAA, recto ad absurdum. So it won't take you too long if you have an inconsistent set of axioms to sort of figure out, well, I've just proved 1 equals 0, which I happen to know is false. So this system is inconsistent. So there's a whole study of logic as to what it means for systems of axioms to be consistent versus inconsistent. There's a definition in logic about inconsistent axioms, and Lean will help you find inconsistent axioms quickly. Yes?
So what would assuming that you are not a math nerd, which I know you are.
Yes.
And I love the hell out of that. What would be situations where this would be a particularly useful language? So what types of things would be people doing, assuming we're not, or is it largely, I'm assuming it's not largely a recreational math tool?
Well, I mean, there are professional mathematicians, and it's not used that much right now, but actually I'm going to address this.
Okay, great.
Actually, that might be the next slide.
Josh, I have a
Josh?
I hear you.
Question?
Okay.
yeah. I was just going to say the use case I'm thinking about with this would be like, I have a lot of questions, like I mentioned, about embedding spaces and the viability of embedding spaces for like how they affect error and learning of algorithms. And a tool like this could do a lot to prove that the methodologies I'm applying aren't dangerous or inappropriate.
It's just math, though. Anyway, yeah, let's go ahead and.
Yeah, I mean, there is an argument that it is just math, but math is a research study, and it's sort of the queen of sciences, right? There's not much science you can do without a foundation of math, because otherwise you're just waving your hands.
Yeah.
You can argue facts till the cows come home, but you can't argue with numbers. Things that you can measure make the difference between doing real science and doing, identifying dinosaur bones. Not that that's not real science. It's just, I remember when I was a kid, I was very frustrated by science classes because there were never any numbers in them. It's like, how am I supposed to know if something's right or wrong? You're just telling me stuff. You know, I was happy to hear that the boiling point of water was 100 degrees Celsius. But, you know, hearing about how water evaporates, just like, okay, but, you know, why? All right, so what's going on here? How do I get, let me just close this window here. Hopefully the other window will come back. Okay, there it is. I mean, really, how can you, one thing I didn't mention is that when you're writing a theorem in Lean, theorem is actually just syntax sugar for function, for a definition of a function. So how can a function be a theorem? And the answer is this very deep idea known as the Curry-Howard correspondence. So this is a good Wikipedia rabbit hole to go down. But what it says is there's a fundamental relationship between logic and computation. The Curry-Howard correspondence, it connects types to propositions. So types like you use in languages. Anyone use Rust or TypeScript? Okay, so these are languages that are heavily typed. Types matter a lot. And there's sort of an algebra of types, right? Like Rust supports vec, but not just vec, you have to give it another type. So vec is actually a metatype because it operates on another type to give you a type, right? You have a vec of U8s or a vec of U16s or whatever. So in Lean, there's a type that corresponds to the statement, the proposition that adding 0 to n gives 0. And the way that you prove it is you write a function that has that type. And that's the fundamental idea between the Curry-Howard correspondence. And now, checking your proof is really just a type checker. So Lean has a very smart, very advanced type checker in it. And these proofs have certain types. All that stuff where I wrote by and RFL and simp and whatnot, that actually turns into a function. And it doesn't really do much because it takes the type and it returns the type. And in functional programming languages, types are erased at compile time. They're basically just sort of hints as to what values can be passed into functions. But when you compile things, you know, you're just dealing with metal. You got a von Neumann machine there with registers and memory and whatnot. You don't know what a string is. You don't know anything. It's all just bytes. So the types go away, but they do provide you a framework to give you reassurances that your code will work because it's not doing crazy garbage like trying to add a string to a float. Where's the cursor? Or maybe I don't need it. Yeah, okay, so proof verification becomes type checking, which is what I was trying to say before that point came up. So here's an example. Say that we know that all cats are mammals. With this Curry-Howard correspondence, that's like saying we have a function f that takes a proof that a thing is a cat, you feed it into f, and what comes out is a proof that that thing is a mammal. So the first statement, that all cats are mammals, that corresponds to assuming that you have this function f that turns a proof that a thing is a cat into a proof that that thing is a mammal. Oh, okay. That's what I was just saying. There's this little view here as to what's coming up. I should really start looking at that. Okay, so I talked a bit about tactics mode. I think I discussed these points already because my notes say that it's like a maze. Tactics gives us a way to navigate the maze from both ends and meet in the middle. Okay, so this is what we've discussed so far. Formalization example of natural numbers, translation of that example to Lean notation. You can try this yourself. There's this thing on the web called the natural numbers game. So search for Lean natural numbers game. And it's got a bunch of interactive puzzles that let you practice foundational math concepts using Lean 4. Where's the cursor? I need to click on a link here. I still haven't figured out where this screen sits in relation to this screen. Is it off to the left? Yes, it is. Okay, great. It's off to the right. Rather, this screen is to the left of it. So let me open this link. God, let's see how long this takes to load. Okay, it's loading. Oh, it's so exciting. Okay, so this is the natural numbers game. It's really fun. If you like puzzles and you like math, then you'll probably not be able to stop playing this. But essentially it teaches you lean. It's fairly interactive. It starts out with some very simple tactics and very simple puzzles. The first one I think is like prove that 37x minus q equals, or plus q equals 37x plus q by executing RFL. So all right, RFL, execute, and look, I did it. So there's a lot of hand holding, so it's a good way to learn natural numbers from first principles. And so it uses the same mechanism where it defines this next function. They call it suck. That's the sort of traditional, it's short for successor. That's with 2 C's, not a CK. And then you build addition. So addition is just repeated bumping, right? Like when I add 3 to 5, what I'm saying is, please bump 5 3 times. So bump, 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 now it's 8. And multiplication is repeated addition, right? So like when I say multiply 2 by 3, I'm saying take 3 and add it to itself twice, bump, bump. Well, that's not bumping, I guess that's plus, plus. And then exponentiation is repeated multiplication and so on. And so you actually go through this whole rigmarole, and you show that, one thing that's interesting is you show that arithmetic is commutative. So a plus b always equals b plus a, right? Everybody knows that. It's like, if I got 3 things in this hand and 5 things in this hand, it doesn't matter if they all end up in the left hand or the right hand, it's going to be 8. Multiplication is commutative. 3 times 5 is 5 times 8, right? Doesn't matter. You got a rectangle, that's 5 times 3. Doesn't matter if you rotate it this way, it's still 15. 15, right? But exponentiation, which is just repeated multiplication, and you know multiplication is repeated addition, is not commutative. 2 to the 3 is 8. 3 to the 2 is 9. What the hell's going on? Why don't we get commutivity now? Multiplication, exponentiation is to multiplication as multiplication is to addition. Why did the commutivity go away? I don't have an answer for that, but maybe the natural numbers game will. Okay, so why would anyone care? It's mostly mathematicians who care. But this I found very interesting because I work for a company called Chia Networks, which has a Bitcoin-like blockchain. And my job there, I was responsible for writing the smart contracting language. So this is, you have to create a new language for contracts because there are certain constraints, mostly denial of service constraints. You don't want somebody able to write a contract that they spend their coin and then the program that checks to see if the coin, the program basically checks to see if the coin is allowed to be spent, right? So you don't want that program to loop forever, because now when you're validating to see, oh, is this spend legitimate? You're just looping forever. But you don't want to say, okay, try running the program for 5 seconds, and if it hasn't stopped yet, just kill it and say, all right, the spend didn't work. Because if I got a really fast computer, maybe the program will finish. But if I don't, maybe it won't. And we want everyone to see the same view of the blockchain. So essentially what you have to do is you have to write a language where every operator has a cost, and you keep track of all the costs that have been incurred. And once you exceed the cost limit for that coin spend, you say, okay, you've failed, you've exceeded the cost. And that's deterministic. It doesn't matter how fast your computer is, because that cost corresponds to operations that you're running and not CPU time or wall clock time. Anyway, so I kept this language as simple as possible. It's sort of a Lisp-like language. Minimizes side effects. It's totally functional, just like Lean, where what comes out of a function only depends on what goes in. There's no reading files. There's no looking at the wall clock. And one thing that's useful with cryptocurrency is making sure that no one can steal your cryptocurrency. Because if you have cryptocurrency, you want to be in control of it, right? So these contracts, auditing them is really helpful. You want to be able to prove that it's impossible to steal money for some value of steal money. Right? These contracts can be complicated. Like you can set up what's like joint accounts where Josh and I have control over coins that are in a particular account, but maybe he's rate limited, so he can only spend a certain amount, and I can spend it as quickly as possible. And so this is, you can see how this is a fairly complicated contract, and you want to be able to prove that the restrictions on him are legitimate and there's not some mistake which just lets him take all the money and spend it. So I have been spending actually months re-implementing the smart contracting language. How do I get, what did I do here? And, oh geez. Somehow I got out of sync. Oops. F, there we go. It helps to say the key you're pressing. I don't know what's going on here, but now I'm not controlling this window from that window. Okay. This is the speaker view. I'm using reveal.js, by the way. Never used it before, but despite all the problems I'm having, I like it. Like I said, I'm a command line guy. Well, I don't want to use like PowerPoint or anything Microsoft really. Okay. It's reset my timer, so I don't know how much time I have left, but whatever. Okay, this is what I was trying to open. And now I gotta drag it back over to this screen. Ugh, so heavy. So this is the project that I've been working on, and I can just poke around here. I'll open up this. So one thing that I proved is two's complement works. If you have a large number, so the smart contracting language supports arbitrarily sized integers. So it doesn't wrap around at 2 to the power 32 or whatever, it just expands. But that means that you have to store your bytes store your integers as a stream of bytes in two's complement format. So I had to prove that that actually works, that you can take a number that's really large, just cut it up into bytes, sign extend it, and then there's a way to take that and then turn it back into a number. So basically that round trip works from a number to a string of bytes and then back without ever changing the value. And that's what this proof does. So it's amazing how many things that you just take for granted when you're taking large numbers and serializing them and then deserializing them later and expecting you're going to get the same thing. There are so many steps that your brain just sort of skips over, because I don't know if there's a way to make this much shorter. But here's the final theorem. It's called round trip two's complement. If you have Z, which is an integer, I'm Canadian, Z, and you take an int and turn it into a two's complement, so that gives you a string of bytes, and then take the two's complement and turn it back into an int, you get the thing you started with. And then so there's a couple cases. 0 is a special case, negative is a special case, and that's proven in a theorem above, round trip two's complement negative. And then positive is a simpler case, but it's also proven in round trip two's complement positive. So you can look, here's the proof of round trip two's complement negative. And you can see there's a lot of Unicode here, like weird stuff like this down arrow. I actually don't know what this tactic or that proof does. That's an implication. Anyway, so Lean right now, it's much better at doing math. A lot of this stuff, there are things that are missing, like you would think that someone else would have proven this by now, but I wasn't able to find that. It's more a computer science thing than it is a math thing. How do I switch to, come on. Oh, I guess I just got to close this window. There we go. Okay, now let me talk to you a bit about how it affects mathematicians, which is probably slightly less interesting to most of you, but cranks and clueless folks have sort of spoiled math for amateurs, because people are always thinking that they've squared the circle or trisected an angle, or what happened here? Oh look, I've run out of power. Well, maybe that's a sign. Let's just skip over this. But Lean lets mathematicians, in summary, I'll just summarize this quickly. Lean lets mathematicians work in larger groups rather than being forced to work with people you trust, are going to be able to produce correct proofs, because you can work with someone that you don't know or don't trust, because if they give you a proof, you can just run it through the lean compiler and say, oh yeah, this isn't bullshit, this is real. LLMs, I think, will be really interesting, because LLMs, they like to try and solve math problems, and it's hard to know. Like LLMs, I've noticed, they can drift into bullshit in a way that is almost imperceptible. And you're reading along, you're like, wait a sec, this doesn't make any sense now. This is all made up. And if you have an LLM that's trying to produce a lean proof, then you can run a compiler and check it. So that's one reason LLMs are so great with typed languages, is because typed languages are good at smelling BS. All right, so this is what we discussed. This is the end of the presentation. Any more questions?
I have a comment.
Hold up. We know the rules here. We live in a society with 2 microphones.
I was waiting for the microphone. I just wanted to say 2 things. One, this was super, super interesting, and also, you're the bravest person I have ever seen. Not only did you do a live demo, you did it literally with one hand, and that was pretty amazing. So that was cool. Do you have more follow-up questions? I know you had asked some before.
No, I think we can you explain a little more about how RFL, or what was it?
Yeah, RFL. That's
Yeah,
right.
RFL.
Reflexivity, it stands
Yeah,
for.
reflexivity. Is that like reflexivity in
Yes, it's like it's
Like
it's hinting at
commutativity,
the idea
like the
of
same-
mathematical reflexivity, which is
Okay.
the notion that a thing is equal to itself.
Can you provide some insight on how that was being used in the theorems and proofs? It didn't really resonate with me as much as I would have expected it
Yeah,
to.
the RFL tactic is a weird one, because it has a ton of intelligence built into it. So what it does is it basically tries to finish the proof. So if RFL can't finish the proof, it says, I didn't make any progress. So it applies a ton of simplifications, a lot of magic. I don't know enough about that tactic to know exactly what it's doing. But essentially, if it can end up with something of the form A equals A, where A can be a really big expression, but it has to be the same on both
So
sides.
if you think
then it says, I'm
you're
done.
right there, and there might just be simplification between you and the answer, just RFL it
Yes.
and then rely on
Yes,
the
there's
compiler.
a lot of simplification, and the scope of that simplification I don't have good insight into.
Oh, that's really interesting. Is there a way to expand the steps completed by RFL to see what it did?
I don't know about RFL. Probably RFL does simp, and simp is a mega tactic. Simp is simplification. As I mentioned, it's simplification, and it's trying to turn terms into a canonical form. So a way that's most likely going to be, if you can turn everything to a canonical form, then it's usually quite easy to see if they're the same, because they only have one canonical form.
Yeah.
But simplets is expandable. You can create your own rules and add them to simp. So if you can import a file from a library, and it expands what simp does.
Very interesting. Thank you so much.
Yes.
Sorry. So I was curious, does it have any handling for subtypes? So for example, would it be able to recognize that a real number is an instance of a complex number, and then that kind of gives you a problem of, okay, I have this
Right.
number 3, is
So
it
here's the
a
problem.
complex number? Or, yeah.
Here's the problem. From a mathematician's standpoint, a real number is not a complex number. What you have is you have 2 separate fields, and the real numbers can be embedded in the complex numbers. So it's like you have a larger field called the complex numbers. You can take a subset of that, where all the operations still give you the same values, but they're trapped sort of basically on the real number line, right? Because the standard operations, multiplication, division, addition, subtraction, exponentiation, you can never get off the real number line, even though all those values are still the same in the complex numbers. So when you make a statement like for all n, addition of 0 and n is n, you got to know what universe you're talking about with that n, because maybe that a statement of the form, let's just call it p of x. For all x in real numbers, p of x is true. But for all x in complex numbers, p of x is not true. Like, for example, if p of x is x squared is greater than or equal to 0. Because there are complex numbers that are negative, whose squares are negative, right? That's how you get complex numbers.
All right. Well,
So I don't know if I've answered your question, but
we're basically at time, so some good news.
okay. Thank God.
First, round of applause. Round of applause. Thank you, thank you. So I'm excited that this is. So I launched a crypto coin on Binance, and the ability to
wow.
use something like this to go through and test all of the logic. Holy cow, that's neat, man. That's neat.
Yeah, it's hard though.
It looks like a real pain in the balls. So the last little bit that we do here is just sort of open mingle anyway, and it sounds like there's still some questions. But this was pretty good. This was pretty good. First Sin City programmers, if anybody wants to present or anything else, feel free to reach out to me. I have a card, and you can email me, and we can get you set up. Excellent. And with that, we're done. Yay!